So what's happening is that we have what's called an open circuit. Open circuit, these two wires need to touch each other here. Here they're touching, and then we conduct electricity. So air is an insulator, so this is why it's not conducting any electricity. We can see if we put this into contact with anything that conducts electricity, the light bulb will light up. Deionized water doesn't conduct electricity, nor does ethanol. So these are the scenarios we have here. Now, the names we use, here I'm going to jump a couple of slides. We can give it different names. Like, for example, this would be a strong electrolyte. A strong electrolyte because it conducts electricity well. So what is conducting electricity? It's the ions. The ions are transferring the charge from the two electrodes. One electrode is positively charged, the other is negatively charged. So the negative ions go to the positive electrode, the positive ions go to the negative electrode, and then we can conduct electricity. So we see the light bulb light up. Well, we got these ions. So for example, this is potassium chloride. Potassium chloride is a strong electrolyte because when potassium chloride is dissolved in water, what happens is potassium chloride is an ionic compound. The lattice breaks apart. What does the lattice look like? Let's take a look. So we'll just see the KCl crystal. Looks like this. So in water, this lattice breaks apart and frees up the ions. Those ions now are mobile and they can conduct electricity. How about solid? If I put solid potassium chloride in contact with the electrodes are those wires. So the positive electrode here, the negative electrode here, will solid potassium chloride conduct electricity? No, it doesn't conduct electricity. Why not? Can somebody tell me why solid potassium chloride does not conduct electricity? Do solids have, what kind of motion is available? Vibrational motion, yeah. What else? What are the three types of motion? Rotational and translational. Solids don't have translational motion. So if I put an electrode here and electrode here, are the ions going to move? No, they don't because there's no translational motion in solids. Whereas in liquids, there is translational motion. We have. And so, let's go on here. So this is why we see electrical conduction here. We give three categories to this. Strong electrolytes are substances that when dissolved create a lot of ions because there's, well, we'd say nearly complete ionization. Ionization is what? The breaking apart of the lattice, or dissociation. Dissociation and ionization is the same kind of thing. Ionization just means it breaks up into ions. Dissociation means the lattice of ions breaks apart. Dissociation. Weak electrolytes, we saw that we have limited, some of these species break apart. Non-electrolytes like ethanol, nothing breaks apart. And so that's something we consider. When something dissolves in water, does it break apart completely, partially, or not at all? Complete is strong, partially is weak, not at all is none. So the order is off for me here because the first thing I consider is, does it dissolve in water? First thing I consider. And so all you need are these key words. Strong is, for lack of back it out here. Strong is complete, weak is partial, non is none. That's all, just those key words. You don't have to write the whole definition. None. Complete, partial, none. Not at all. So the situation is, we gotta know if it dissolves or not. Well, dissolving is called solubility, and that's way at the end of this chapter. So let me jump way to the end of this chapter. A long chapter. And so here we have solubilities of ionic compounds. Like, for example, aluminum acetate, they say slightly soluble. Slightly soluble means a little bit dissolved. Aluminum bromide is soluble, which means a lot of it dissolved. Aluminum carbonate does not exist. I don't know why they did that. Aluminum chlorate, soluble, etc. So we have this chart here. This chart comes from actual data. Aluminum carbonate. Where does that data come from? That data comes from experimental data. Experimental data, actually Wikipedia is pretty good for just this type of data. Otherwise you have to buy a book. A book that compiles all this data. And so let's look at aluminum carbonate. Here, Wikipedia. Aluminum carbonate is a carbonate of aluminum. It is not well characterized. One authority says that simple carbonates of aluminum, gallium, and indium are not known. Basic sodium aluminum carbonate mineral dawsonite is a known compound. So, varieties of this. So there's no data here for this. Because I guess this is not a very stable compound itself, so that's why they say it does not exist. Because people try to make it, but it's not so stable. But we could go to a different one. For example, aluminum bromide is the other one. So let's look at aluminum bromide. Here's the next one. This one is tricky. It's tricky because look at the structure. Is that a molecular structure or is that a crystal lattice structure? Molecular structure. That's because it gets tricky because aluminum is at the border between what and what? Non-metals and metals. Right. And when you're a non-metal, you like to form molecules, but when you're a metal, you'd like to form ions. So when we're in this zone here, let's see, where did my periodic table go? There's too many things up in here. There it is. When we're in this zone here, it gets a little bit tricky to figure out. If we're here, metal and a non-metal, we're going to get an ionic lattice. But, you know, are these becoming more and more metallic as we go over here? So, for example, tin. Tin, is that, you know, the most metallic? Tin is starting to transition because, let's say, indium's a metal, cadmium's a metal, tin is a metal, but antimony, is that considered a metal? And so what happens in the period is it's much more metallic over here. As we go across, it becomes less and less metallic and more non-metallic. Eventually, it transitions all the way to non-metallic. There's a gradual transitioning from metallic to non-metallic. When we're in these semi-metal regions, then we have a choice. It might be ionic, it might be molecular. It's tricky. So, for example, lead. Lead is in this region here. It turns out lead-2 chloride is an ionic lattice, but lead-4 chloride is molecular, forms molecules. And so things get a little bit more tricky around here. You have to be aware of that. But you know how to predict it? We aren't going to predict it. You know, it's just what's observed. And so let me pick out a simpler one. So, for example, if I look at ammonium acetate is soluble. And so let's go over here. How soluble is it? Well, it just says soluble. And so, does that mean it's totally soluble or what? Let me just see if I have it here. And so what I do is I go down here and you see this box here, solubility in water. So this tells me how soluble it is. It's actually quite soluble. Let's say at 20 degrees C, which is close to room temperature, I could dissolve 143 grams of ammonium acetate in 100 milliliters of water. It's a lot. And so since it's a lot, we call it soluble. And so solubility, well, we aren't going to nail it down to that. Versus table salt. Do you think table salt is more soluble or less soluble than ammonium chloride? Okay, keep this number in mind. 143 grams per 100 milliliters. Now, what do you think? Is table salt soluble in water? Like if you take some salt, like put some salt in and make salt water, it's pretty soluble. Change the units here. All right, so this is soluble. It's 360 grams in a liter. So what that means is it's going to be 36 grams per 100 milliliters. 36 grams per 100 milliliters versus 143 grams. Which one's more soluble, ammonium chloride or table salt? Not ammonium chloride. Ammonium acetate or table salt? Ammonium acetate's a heck of a lot more soluble. But table salt, you know, 36 grams per 100 milliliters is very soluble. How about, that's table salt, NaCl. How about silver chloride? Let's take a look at the solubility for silver chloride. If I look at the solubility for silver chloride, I have 520 micrograms per 100 milliliters. 520 micrograms, is that pretty soluble? No, it's not. In 520 micrograms compared to 36 grams, compared to 143 grams, is quite a big difference. And so what we're going to do is we're going to call silver chloride insoluble because so little of it dissolves in water. And then we'll call table salt and ammonium acetate soluble. But where does it transition? Where does it transition from being soluble to insoluble? Where it transitions is this, around 0.1 moles. If we could put 0.1 moles in a liter, then we'll call it slightly soluble. If we can get more than 0.1 moles in a liter, we'll call it soluble, and less than 0.1 moles in a liter, we'll call it insoluble. And so what we're going to have are very broad categories of solubility. And so this is what they did here in generating this chart. In generating this chart, 0.1 moles is, it depends on how much it weighs, the molar mass. But this is about 0.1 moles per aluminum acetate is about 0.1 moles per liter. All these are greater than 0.1. All these are less than 0.1. That's it. And then we're going to have 3 categories. Actually, this has more than 3 categories. This has 3 categories. Three categories would be soluble, slightly soluble, or insoluble. Or they say nearly insoluble because, you know, everything dissolves to a small extent, so that's why. Some things, when they come into contact with water, decompose. They react with water itself. So that's why it says decompose with water. Do you want to memorize this table? Actually, this is page 1 of the table. You want to memorize page 1 and page 2 of this table? No, it's too much, right? But this is better than memorizing the individual solubilities, like 143 grams. Do you want to memorize that? No. And so what we're going to do is we're going to come up with a simpler list. If this is too much to memorize, we look for patterns. And now, is there a pattern to this? There are patterns to this. And so what we're going to do is we're going to just try to memorize a simple pattern. And so this is called the solubility rule. For ionic compounds. So what is the pattern here? This is rules. Are rules perfect? No. Rules are going to have some exceptions. We'll live with those exceptions. If you want to make absolutely sure, then check Wikipedia or something like that, you know. But the rules are going to go like this. First, you check the cation. And we see that group 1 and ammonium salts are soluble. Salts meaning, you know, ionic compounds that aren't acids. You know, so a typical salt is a metal and then some kind of anion, non-metal anion. So group 1 and ammonium salts are soluble. Salts. Group 1 and ammonium salts are soluble. Like sodium chloride. Sodium is group 1. Sodium chloride is soluble. Ammonium acetate is soluble. Silver chloride is different. Is silver? No, silver is not group 1. It's not ammonium. So first you look at the cation, and then you look at the anion. When we look at the anion, then these solubility rules are from your lab manual, not from the book. When we look at the anion, then we're going to see a certain pattern, like, for example, nitrates, chlorates, and acetates. I should probably do nitrate, acetate, chlorates. Chlorates aren't as common. Doesn't matter in the order. Nitrates, chlorates, acetates, these are all soluble. When I say all, you got to keep in mind these are rules. There could be exceptions, but there are very few exceptions. Okay, the next anions we look at are the chlorides, bromides, and iodides. Chlorides, bromides, iodides. What's missing here? The fluorides. The fluorides are too many exceptions here. If I put fluoride here, the best thing to do for fluorides is just look it up. If you have a fluoride, look it up, because otherwise it's too many to memorize. These are soluble, except when paired with silver ions. So for example, silver chloride, silver bromide, silver iodide are insoluble. Lead-2 chloride, lead-2 bromide, lead-2 iodide are insoluble, and mercury-1. Mercury-1 chloride, mercury-1 bromide, and mercury-1 iodide are insoluble. Those are insoluble. Unfortunately, we have to memorize these. But this is a lot easier than memorizing Wikipedia, which is a lot easier than memorizing this. Well, this table is a lot easier than memorizing Wikipedia, and these rules are a lot easier than memorizing the table. look at, after this, we look at sulfates. Sulfates are soluble, except when paired with silver. I'll put a little asterisk because with silver sulfate, it's slightly soluble. Silver, lead 2, mercury 1, mercury 2, calcium, strontium, and barium. Plus. These are insoluble. So for example, calcium sulfate turns out to be insoluble, whereas iron 3 sulfate is soluble. Not one of the exceptions. For the most part, soluble sulfates are soluble. And then we go to hydroxides. Hydroxide compounds are soluble, or hydroxide salts are soluble, except hydroxides are not soluble, sorry. Hydroxides are insoluble. And so the first 3 are soluble. The next 3 are going to be insoluble. And so we're going to shift. Hydroxides, most hydroxides turn out to be insoluble, except there are some that are, like for example, group 1 and ammonium. Hydroxides are all soluble. And calcium, strontium, and barium hydroxides are soluble. So these ones are the exceptions. These are soluble hydroxides, but for the most part, most hydroxides are insoluble. The next category are sulfides. Sulfides are insoluble, but there are some exceptions, except group 1 and ammonium, group 2, and then that's it actually, just group 1, group 2, and ammonium. So magnesium sulfide is a group 2, it turns out that's soluble. But manganese sulfide, manganese 2 sulfide is insoluble. Okay. And then one more. The one more is going to be phosphates. Phosphates are going to be insoluble, except group 1. Actually, not just phosphates. Phosphates, carbonates, and chromates are insoluble, except group 1 and ammonium. So this is kind of the pattern that we see in this chart here. So let's try to use this briefly here. So typically, what do we look at first? We look at the cation. Is a cation is group 1 or ammonium? They're all. So look at ammonium. Doesn't matter what we put ammonium with. Ammonium acetate, ammonium bromide, ammonium carbonate, ammonium whatever. They're all soluble. And so ammonium, let's see, sulfide soluble. Ammonium sulfide soluble. What else should be soluble? Well, what are group 1s? Let's take a look. Are there any group 1s here? Yeah, there's 2 group 1s. One group 1 is lithium. That's a group 1. So lithium are all soluble, although this one's borderline. What is this one here? Fourth one over. lithium phosphate. Lithium phosphate's borderline. And then we go to sodium. All sodium salts are, take a look, soluble. Potassium's group 1. All potassium salts are soluble. Do you see that? Okay, then if it's not group 1 or ammonium, then what do we look at? Well, why would lithium phosphate be an exception? Well, there's more patterns to this. We'll see. Okay, if it's not one of those, group 1 or ammonium, then what? We look at the anion. So what are the anions? What's the first anion we check for? Nitrates, acetates, and chlorates. All right, so let's take a look at the anions up here. All right, here we have chlorates. Aluminum chlorate, ammonium chlorate, barium chlorate, calcium chlorate, cobalt 2 chlorate, copper 2 chlorate. They're all soluble. Chlorate's a fourth row. Lead 2 chloride, lithium chloride, magnesium, nickel 2, potassium, silver, sodium, zinc. They're all soluble. That's chlorate. Okay, then what else do we look for? Chlorates and nitrates and acetates. Well, here's acetate here. Except here, the aluminum's like borderline, right? Aluminum's right at the edge. Aluminum. But other than that, all the acetates are soluble. Except silver is kind of borderline, but you know, these are rules. These aren't perfect. It's all right, we can live with it here. So that's the acetates, and then what was it? Acetates, chlorates, and nitrates. Let's look at nitrates. Here are nitrates here. We look at all green. Nitrate. Let's drop down to the next page. It's the fifth one from the end. Sixth one from the end. All these nitrates are soluble. Okay, if it's not one of those, then what anion do we look at next? Look for chlorides, bromides, and iodides. Chlorides, bromides, and iodides are all soluble except for which ones? Except for silver, lead, and mercury. So is there any silver, lead, or mercury here? No, and so take a look. Chlorides are all soluble. Chloride is the fifth one. Yeah. Is there any silver, lead, or mercury here? Yes, here. Lead 2. So lead 2 chloride should be insoluble. Well, it's borderline here. And here's silver. Silver chloride should be insoluble, which it is. But the rest are soluble. That's chlorides. And then we go to bromides. Soluble. Except for lead and silver. then finally, iodides. We're going to take a look at the iodides. Iodides are soluble except for lead and silver. Okay, after the iodide, well, what about fluorides? Remember we left off fluoride. Problem with fluorides is, if you take a look at fluorides, there's too many exceptions. Do you want to memorize each of these exceptions individually? No, so fluorides is a bit more hassle. And so what we're doing is we're just trying to break this chart down into a simple set of rules that are a lot easier to memorize than the chart. Uh-huh.
So for the test, would you give us like a chart and like what we have to fill out, like if they're soluble and maybe soluble, or would you like ask us a question of which one is soluble?
Both.
So you'll make this up?
Right. Well, I'll give you a compound and ask you if it's soluble or insoluble. Like for example, I'll just pick a compound. Let me pick a compound: iron, iron 3 acetate. Soluble or insoluble?
Soluble.
Soluble. Iron 3 carbonate. Soluble or insoluble?
Yeah. Soluble.
Well, you know, if I do iron 3 carbonate, it says does not exist. We're looking at that aluminum here as well. But if I said iron 2 carbonate, you would say insoluble. You don't need to know it at this level, you know, but you'd say carbonates, if it's not an exception, you'd say it's insoluble. Insoluble. And so, yeah, what you have to do is you have to have these rules memorized and know how to use them. That's all. That's what we're doing here. Well, this is what we have to pay attention to, these little footnotes. Let's read this footnote. Compounds having solubilities of 0.1 moles or more in a liter of water, 20 degrees C, are listed as soluble. If the solubility is less than 0.1 moles per liter of water, the compound is listed as slightly soluble or nearly insoluble as appropriate. Both slightly soluble and nearly insoluble compounds are solids in net ionic equations. No ionic compound is entirely insoluble in water. You know, a little bit will dissolve, even if we classify this insoluble. So we'll have different designations. So you need to read through the footnotes as well. Okay, so we jumped ahead to solubility. Now we're going to jump back to electrolytes. When we look at a compound, we look at two things. One, this is it. Is it soluble in water or not? And two, if it's soluble in water, does it break apart completely, partially, or not at all? Those are two things we look at. One, is it soluble? Two, does it break apart when it dissolves in water? Okay, to answer the first question, is it soluble, we need the solubility rules. This is the solubility rules for what we call ionic compounds. There's one more set of solubility rules that aren't listed here. But the one more set is solubility rules for molecular compounds. These solubility rules for molecular compounds are a lot easier to remember, and it's just called like dissolves like. We don't know enough about structure to really use this rule completely. That's why it's not discussed in this chapter. We need the structure of the molecules. So for example, oil and water, are they similar or are they different? They're quite a bit different. So oil and water don't mix. Whereas something like ammonia and water, they're somewhat similar in certain respects, so they mix. And so oil and water, not good. But oil and oil is good. What's happening? So the first question is, does it dissolve in water? Okay, sodium chloride. Sodium chloride, we first look at the cation, group 1, and ammonium. Sodium is called a group 1 alkali metal. So this is soluble in water, so it dissolves. It's question 1. Question 2 is, when it dissolves, does it break apart completely, partially, or not at all? Now, how do we know if sodium chloride breaks apart or stays together, or partially breaks apart? Well, let me give you some rules for electrolytes. Again, these are rules. It's not always perfect, but if we want to know exactly, we would look it up in more detail. Okay, how we know if it breaks apart or not is this. One, we first determine if it's a strong electrolyte. Strong electrolytes are these. The strong electrolytes, there are 3 of them. 1, is it a soluble salt? All soluble salts are strong electrolytes. So sodium chloride, is it a soluble salt? Yes, therefore it's a strong electrolyte, therefore it's going to break apart completely. So here we need to know the solubility rules. So know solubility rules. Salts are ionic compounds. Just another, you can call it an ionic compound, but it gets a little long. I'd rather just call it salt rather than an ionic compound. Sometimes. Not all salts are soluble. They're insoluble salts. So for example, silver chloride is an example of an insoluble salt. So it doesn't dissolve in water. We wouldn't be breaking apart. The definition is a little bit more complex. The strong acids. Here we have to memorize the 7 common strong acids. The 7 common strong acids are as follows. HClO4, HClO3, HI, HBr, HCl, HNO3, H2SO4. Can you name these? As acids, name them as acids. Hydrochloric acid is which one? The first one? No. HCl. This is a hydrochloric acid here. This is a hydrochloric acid, that's hydrobromic acid, this is hydroiodic acid, because hydroic means ide. So chloride, bromide, and iodide. Chloride, bromide, and iodide are going to form the hydro. None of these others. What's this anion here? That anion is ClO4 minus. What do you call ClO4 minus? Well, we have to look at chlorine. We've got to look at the periodic table. So look at the periodic table here to figure it out. My periodic table. I gotta start closing some of these tabs. Way too many of them. All right. Just having trouble here. I'll look at the periodic table. What do I look for in the periodic table? I'll look for two things. What two things do I look for when I'm trying to? I look for somebody tell me, if I'm trying to name oxyanions, what two things do I look for in the periodic table? Two oxyanions. I ask you to memorize these two eights. What are they? Borate. Yeah, borate. And what's borate? BO3, 3 minus. So this is BO3, 3 minus, this is CO3, 2 minus, NO3, 1 minus, FO3, 1 minus, ClO3, 1 minus. ClO3, 1 minus. ClO3, 1 minus is chlorate, therefore ClO4 is, this is perchlorate. And this would be called perchloric acid. This is ClO3 minus. This is called chlorate. Therefore, this acid would be called chloric acid. So this is perchloric acid. This is chloric acid. Hydroiodic acid, hydrobromic acid, hydrochloric acid. What's HNO3? BO3, 3 minus, CO3, 2 minus, NO3. 1 minus is nitrate. And so therefore, this is called nitric acid. And then finally this one, SO4. SO4 is not in this, it's here. For this one, we start with silica, which would be silicate. What's silicate? SiO4, 4 minus. So this is SiO4, 4 minus. This is, yeah, good. PO4, 3 minus. And then sulfate would be SO4, 2 minus. So this is sulfate. And so therefore this is going to be sulfuric acid. So those are you have to memorize the 7 common strong acids. And then there's one more thing here. This would be the strong bases. Let me just, actually we're out of time. I'll just do it next time.